A burner nozzle lives at the exact point where fuel becomes flame. A place that runs past 1,500 degrees and never cools for long. A metal nozzle there slowly warps, oxidizes, and loses the shape that aims the fire. The long gray cone turning here was made for that spot. It holds its mouth and its flame steady while the heat that would melt steel barely marks it. What a burner nozzle fears most is not heat itself but sudden change. Light the flame or shut it down, and the tip swings hundreds of degrees in moments. Silicon carbide takes it in stride. It can ride a temperature swing of up to 250 degrees a minute without cracking, helped by a thermal conductivity reaching 120 watts per meter Kelvin that carries heat away from the flame front instead of letting it pool in one spot. Strength is the next demand, and it has to last while glowing. Where metal softens and droops at flame temperature, silicon carbide keeps most of its strength past 1,400 degrees, so the nozzle holds its bore and its aim instead of sagging out of true. Its extreme hardness adds a second defense. The abrasive dust and particles riding the gas stream scour past without rounding off the orifice that sets the flame. Then there is the atmosphere of combustion itself. As it heats, silicon carbide grows a thin, self-renewing layer of silica that seals the surface and slows further oxidation. So it does not scale and flake the way metal does. That same skin shrugs off the chlorides, sulfur compounds, and grit in the exhaust, letting the nozzle hold a clean, accurate flame long after a metal one would have corroded through. All of it starts in the bond between two light atoms. Silicon and carbon share electrons in strong covalent links, building a rigid, close-packed lattice that is nearly as hard as diamond and chemically almost indifferent. For a burner, the reaction-bonded grade is often chosen. Silicon carbide grains locked together with a little infiltrated silicon, which lets a long, flared shape be formed accurately and fired dense. Two physical traits make that lattice ideal at a flame. It moves heat almost like a metal, so no single point overheats and cracks. Yet it barely expands, only about 5 parts per million per degree. So it does not fight itself as it heats and cools. Add an oxidation limit far above where alloys scale, and the result is a material that treats a blowtorch as a normal working day. Because every burner fires its own way, the nozzle is shaped to the equipment rather than to a standard. Overall lengths reach from a short stub up to roughly half a meter, bore and outlet diameters are set to the gas flow and flame shape, and the wall is sized to the pressure and heat it must carry. The critical orifice and seating faces are ground to a tight tolerance so the flame lands exactly where it should. From there the form follows the duty. The inlet can be plain, stepped, or threaded to meet the fuel line. The outlet can be straight, tapered, or flared to spread or focus the flame. Mounting flanges and seats match the burner block. And the silicon carbide grade is picked for the temperature and the abrasives it will face. Few places test a nozzle like a high-temperature kiln, where burners fire continuously to hold a furnace at temperature while wear moves through. There, the nozzle must aim a precise flame jet through cycle after cycle of heating and cooling, in an atmosphere thick with ash and combustion products. Silicon carbide answers on every count. It keeps the flame geometry stable as the kiln ramps up and down, it holds its shape without sagging at full temperature, and its oxidation and corrosion-resistant surface stays clean where metal would scale and distort. The flame stays where the design put it, hour after hour. Notably, the part sitting closest to the fire is the one that ages the slowest.